in this video, we're going to start chapter 2, which is all about elements, atoms, and the periodic table. So you'll notice in the background, there's a periodic table, and you should be able to find one on our course website so that you can follow along. I will also provide printed copies when we meet in person. So let's start with the elements. Remember from chapter 1, we said that an element is a substance that cannot be broken down into simpler chemical substances. Now, there are about 90 naturally occurring elements known on Earth. And using technology, scientists have been able to create even more elements that do not occur in nature. And it was actually recently that they finished the periodic table. They were able to get all the way up to element 118. So some of those elements, some of the higher numbered elements, were created one atom at a time. Now off to the side, I have some pictures of different elements. So on the left is gold. In the middle, we have iron. And on the right, we have a sample of mercury. Now, every element has a very specific name and symbol. And some of these names come from planets or mythological figures, different colors, or even locations. And some are named after famous people like Einstein. So down below, there are some common names of different elements. So we have uranium, which is after the planet Uranus. The next one is titanium, which comes from mythology. The next one is chlorine, and this comes from the Greek word for greenish yellow, which is chloros. And then you can see some other examples down below. And notice that each element has its own symbol. So uranium has a capital U, titanium has a capital T followed by a lowercase I, and so on and so forth. So some symbols only have one letter, others have two. So let's talk a little bit about those symbols. Now, again, elements, their full name can be difficult to write every single time. So that's why we have symbols or abbreviations for each of these different elemental names. You'll notice off to the side, we have oxygen, which is given a capital O, fluorine, capital F, and neon, capital N, lowercase e. Now, if an element has two letters in its symbol, the first one is capitalized, the second one is lowercase. And some elements are going to have two letters so that we don't get different elements confused. For example, nitrogen has the symbol N. So if neon was also given the symbol N, that would get confusing. So neon was given that second letter to differentiate it from nitrogen. So find that periodic table on our website, or you can just pull up any periodic table online and see if you can find the correct symbol for each element below. So the first one is aluminum, the second one is iron, the third one is gold, and the fourth one is mercury. So pause the video, see if you can find those symbols, and when you unpause, we'll go over them together and see if you are correct. All right, so let's go over these symbols. Aluminum is given the symbol A, L, where A is capitalized and L is lowercase. Iron is Fe, and this symbol doesn't really make sense with the name iron, right? So Fe is coming from the original Latin name for iron, which was ferrum. Gold is given the symbol AU, which also does not match its name, gold. So AU is coming from the original Latin name aurum. And then mercury is Hg. And I'm not even going to attempt to write out the Latin name that goes with Hg, but you get the idea. A lot of these symbols are coming from older names for these elements. All right, so next we're going to talk about atomic theory. So in chapter 1, we said that an atom is the smallest part of an element that maintains the identity of that element. And a chemist named John Dalton proposed something called the modern atomic theory. And this was proposed in 1803, so a very long time ago, over 2 centuries ago. And this is just a fundamental concept that states that all elements are composed of atoms. So the modern atomic theory says that all elements are composed of atoms. Now, individual atoms are really, really small. So even the largest atom has an approximate diameter of 5.4 times 10 to the negative 10th meters. So really, really small. And your fingertip contains about 18 million atoms. So these must be really, really, really small, right, to all fit in your fingertip. Now, most elements in their pure form exist as individual atoms. So, for example, helium, which has the symbol He, that just exists on its own as one individual atom. But some elements are not stable as individual atoms, so they typically pair up with another copy of themselves. So they exist as molecules, and in particular we would call them diatomic molecules, since there's only 2 of them bonded together. So for example, hydrogen does not like to be by itself, so it actually will pair up with another hydrogen atom. Nitrogen does the same thing. Nitrogen does not like to be alone, so it will pair up with a copy of itself. And this is true for oxygen, fluorine, chlorine, bromine, and iodine. So notice that hydrogen is kind of off by itself on the periodic table. It's up in the upper left corner. But the other diatomic molecules form an upside down L off to the side here on the right. So that's one way that you can remember which elements form diatomic molecules. The other way to remember is with the acronym Hofbrinkel. So hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Now, the reason why it's important to remember the diatomic molecules is later on, we're going to start writing out chemical reactions. And we need to remember that hydrogen, nitrogen, etc. will have 2 atoms bonded together because that's going to affect our chemical reactions. So just keep this in the back of your head for now, and it'll come up again later. Now, there are a few other elements that can exist as 3-atom molecules, like ozone. Ozone is in our atmosphere. It protects us from UV rays. You might have heard of the ozone hole or the hole in the ozone layer. So ozone contains 3 oxygen atoms that are all bonded together. And then phosphorus actually forms a 4-atom molecule, P4, and sulfur can exist as a ring where there's 8 sulfurs all bonded together. So that's shown down below here. And off to the side, that's just showing the geometry of the different sulfur atoms. So these are ball and stick models, for example. But you don't have to know these, just know the diatomic molecules. And just in general, be aware that other elements can form larger molecules as well. All right, so now that we've talked about the atom, let's kind of dive deeper into the atom. Now, atoms are made up of 3 subatomic particles, so particles that are even smaller than the atom. And these are called protons, neutrons, and electrons. Now, again, atoms cannot be broken down into simpler pieces, or broken apart, I should say, but they do each contain protons, neutrons, and electrons. So down below I have a figure of an atom, and there's little tiny particles within that atom. And the first particle we're going to talk about is the electron. So this was identified in 1897, so again, a really long time ago. And this is an extremely tiny particle, so its mass is about 9 times 10 to the negative 31 kilograms. So that's really tiny. And experiments with magnetic fields showed that the electron has a negative electrical charge. So electrons are negatively charged, and you'll notice in the figure that they're sort of floating around the outside of the atom. So we call that an electron cloud typically. By 1920, experimental evidence indicated that there was a second particle within the atom, and they called that particle a proton. And protons are also fairly small, but they are more massive than an electron. So their mass is about 1.6 times 10 to the negative 27th kilograms. Now, a proton has the same amount of charge as an electron, but its charge is positive instead of negative. So protons and electrons can attract each other because they have opposite charge. So again, remember, electrons are negatively charged and are floating around the outside of the, or sort of the outer edge of the atom. And then protons are positively charged. And notice that they're in the middle of the atom. And we'll talk about how that was determined in a bit. Now, the last particle that was discovered was the neutron. So this was discovered in 1932, and this particle has about the same mass as a proton, but it does not have an electrical charge to it, so it is neutral, hence its name neutron. So neutrons are shown in the middle with the protons. And again, they do not have a charge. So we just said that protons and neutrons are in the middle of the atom. Now, we call that the nucleus. So the nucleus contains protons and neutrons. So down below, we can see a summary here. Electrons are outside of the nucleus, and they orbit around it because they are attracted to the positive charge from the protons in the middle, in the nucleus. So most of the mass of an atom is in that nucleus, because remember we said that protons are more massive than electrons, and neutrons have about the same mass as protons. Now, electrons don't really contribute to the mass of an atom. They're really, really small. but they can account for an atom's size because they are outside of the nucleus. So how did scientists even discover that there was a nucleus? So originally, there was something called a plum pudding model, where it was thought that electrons, protons, and neutrons were just all floating around the atom. They didn't have a particular spot where they were located. And this was called the plum pudding model because it looked like plum pudding, which is actually more of a cake that contains plums in it. So I believe that's more of a British dessert. I don't think we really have that here in the US, but so this was the plum pudding model. So Ernest Rutherford, who was a physicist at Cambridge, wanted to test this theory. He wanted to prove that the plum pudding model was correct. So between 1909 and 1911, him and his associates, Hans Geiger and Ernest Marsden, performed the following. They set up a piece of gold foil in the middle of a detector. So this was actually a fluorescent screen. And they shot radiation through that gold foil. Now, the thought was that if atoms do follow the plum pudding model, then all of these radiation particles would just go straight through. All of them would just end up at the same spot on the detector. However, what they found was that some of the particles went straight through. So some of them did go straight through, but some bounced and were deflected off to the sides. So there had to be a really dense part of the atom, or a really a spot where everything was really clumped together, for example. So that's how they came up with the idea that there was a nucleus in the middle of the atom, and some of the radiation beams were hitting the nucleus and bouncing off. Or some were just slightly deflected, but some particles did just go straight through because they were passing by the nucleus. So this is how we have our current model of the atom, where protons and neutrons are congregated in the middle and electrons are floating around the nucleus. So let's just summarize what we've learned so far. So we said that protons have a mass of about 10 to the negative 27 kilograms, and neutrons are about the same. So we can actually give them a relative mass of 1. That's a lot easier to think about. Electrons, however, are much, much smaller in terms of mass. So their relative mass is 0.00055. And that's why electrons don't really contribute to the mass of an atom. We also said that protons have a +1 charge. They're positively charged. Neutrons are neutral, so they have 0 charge. And electrons are negatively charged. They have a charge of -1. Off to the side, you can see their symbols. So we can symbolize a proton as P+. Neutrons are N0, and electrons are E-. So you might see those symbols pop up in the future. All right, so I think I'll stop the video here now that we've talked about atoms and their structure. And next time, we'll start getting into the nuclei and how do we figure out how many protons, electrons, and neutrons an atom has. So I will see you then.